Hi everyone. I'm going to start this recording by going over the top hat question at the end of the previous lecture. The question was to calculate the rate of oxidation of a metal at 500 degrees Celsius when the activation energy is given as 328 kilojoules per mole, or 3.28 times 10 to the 5 joules per mole. You're also given the rate of oxidation at 300 degrees Celsius as 1.05 times 10 to the minus 8 kilograms per meters to the fourth seconds. So there are two ways of calculating the rate of oxidation at 500 degrees Celsius. One way is to calculate for C, and then you can calculate the new rate. So here you can see that the rate at 500 degrees Celsius, 573 Kelvin, is 1.05 times 10 to the minus 8 equals the pre-exponential factor, and then e to the minus 3.28 times 10 to the 5 over the gas constant, 8.314 joules per Kelvin moles times 573 Kelvin. And when you solve for C, you get C is 8.37 times 10 to the 21. If you plug in C, you get that the new rate is 5.72 times 10 to the minus 1 kilograms over meters to the fourth seconds. And that's the rate for at 773 Kelvin or 500 degrees Celsius. The second way of calculating the rate at 500 degrees Celsius is to use the set of equations for the rate at 300 degrees Celsius and 500 degrees Celsius. And if you divide the two exponential values, you see that you can get the rate at 773 Kelvin or 500 degrees Celsius to be the same as the first method. Okay, we'll continue with chapter 5 by talking about diffusion in solids. One of the ways that atoms can diffuse is just through self-diffusion. And so atoms move through the solid by vacancy migration or vacancy hopping. And so in the example here, you see that there are atoms in these hollow circles, and the blue highlighted atom will move to the vacancy site after the migration. So you can see here now the vacancy and the blue atom have switched places. And so in the cartoon animation here, you'll see that the blue atoms and the orange atoms will move from their atomic site to a vacant site. And what you'll also see in vacancy diffusion when these atoms exchange places with the vacancies is that now there's a change in the concentration going from left to right. When you have interstitials, interstitial atoms can diffuse through the solid by just moving from interstitial site to interstitial site. And so here I'm just drawing, a random movement of the interstitial atoms. And so clearly, the orange atom doesn't really follow my path because it is random and it can be in any direction. So just as I've mentioned, when atoms start moving around, the concentration is going to change. And in fact, there's going to be a concentration gradient as time goes on. And so here we see the concentration of copper atoms, and that happens to be in orange, plotted as a function of the position in the x direction. You can also plot the concentration of nickel atoms versus the X direction. And so you can see here, there's a lot of copper atoms on the left and fewer copper atoms going towards the right. And so you could show that with this curve here. You could do the same thing to represent the nickel concentration, and that decreases from right to left, as you can see here in the diagram. And when atoms diffuse, they tend to migrate from regions of higher concentration to regions of lower concentration. This is the driving force for net diffusion. So when we talk about the movement of these atoms, the steeper the concentration profile going from left to right, the greater the flux or the greater the flow rate. And we can mathematically relate the flux or the flow rate, or J, of the diffusing species to that of the concentration gradient dc dx. So here, this is called Fick's law, and we can write that out mathematically that you see here. You can see that J is equal to negative D times the concentration gradient dc dx. And we'll talk more about this diffusion coefficient D in a little bit, and it's actually related to temperature. So it changes as a function of temperature. The way one can think about the diffusion coefficient or diffusivity is that it's a measure of how easy diffusion is. So as D increases, so does the flux. Because D increases, J increases for the same concentration gradient, or dc dx. The diffusion coefficient, or diffusivity D, is related to the temperature via this exponential equation. So D naught is the pre-exponential constant, QD is the activation energy for defect motion, R is the gas constant, and T is the temperature in Kelvin. Here, QD is not just the vacancy formation, but it's the defect, it's beyond the defect formation energy. It consists of the energy for vacancy formation as well as movement of the defect through the crystal structure. And if you're talking about interstitial diffusion as opposed to vacancy diffusion, it's the energy that's required to move the defect throughout the interstitial defect throughout the crystal structure. And you could see it's a Arrhenius type relationship where if we look at the log of the diffusivity, so here you could see the y-axis is in logarithmic scale versus reciprocal temperature. You could see that it's a linear relationship in which the slope is negative Q over R. And when we look at the diffusion coefficient or diffusivity for a variety of species in different types of crystal structures, we can take a look at the diffusivity for carbon in BCC iron as opposed to carbon in FCC iron. And you could see that the Q, or activation energy, in BCC is less than that of FCC because BCC is a more open structure, and so it takes less energy to move through this structure of iron. And these values can be tabulated in a variety of databases that you'll find. Your book in table 5.2 puts together data for D naught, as well as the activation energy Q in kilojoules per mole, as well as Q in kilocalorie per mole for a variety of relevant systems, such as carbon in FCC iron, carbon in BCC iron, and so on and so forth. You could see in this other data table that the diffusing species, such as carbon in alpha iron again, or BCC iron, you could see that the diffusivity at 500 degrees Celsius versus 900 degrees Celsius um, can change quite dramatically by 2 orders of magnitude. Iron self-diffusing in itself in a BCC structure going from 500 to 900. You could also see the diffusion coefficient or diffusivity increase by quite a bit when going up 400 degrees. And just as we've talked about diffusion coefficient D or diffusivity D for carbon and iron or iron in itself, we can also track the diffusivity values for cations and anions in ceramic systems. So here you see some examples for magnesium and magnesium oxide, as well as the oxide ions in magnesium ions. And you could see that the diffusivity for the cation is much higher than that of the anion. So we'll jump ahead to talk about the differences in diffusion when we talk about steady state diffusion as well as non-steady state diffusion. When we talk about steady state diffusions, we're talking about processes that occurred over a long period of time, or the diffusion length is a very short distance. So here it's listed as some thin membrane of a material, such as just a sheet of metal or a pair of gloves, let's say. And when we talk about that distance, we're talking about what happens when we set the distance at x equals 0 to some finite distance x naught. And the flux is actually constant. So the flow rate is constant in steady state type diffusion. And so here we can look at it a little bit more clearly, where if we look at a system where you have some fixed gas pressure, that's higher. So here that's denoted as CH over some distance, some short distance, X. And on the other side, you have low fixed gas pressure. So you could see here that in this steady state, we can calculate, DC, what is the change in the concentration over this distance, X. And where this can be quite applicable is in understanding diffusion of chemicals through thin membranes. And here's an example in which we take methylene chloride, or dichloromethane is the other name for it. It's a common ingredient in paint removers. It's an irritant. It can also be a carcinogen, and it can be readily absorbed through the skin once it goes through your glove. And so when you're using paint removers or dealing with dichloromethane, it's advisable that you wear gloves. So one can ask, what is the steady state flux of methylene chloride through this rubber glove that has a thickness of 0.04 centimeters? And we're given here the diffusion coefficient or diffusivity D as 110 times 10 to the minus 8 centimeters squared per second. So in this example, we have the paint remover with a concentration of 0.44 grams per cubic centimeter on one side of the glove. And if it happens to touch your glove that's in contact with your skin, maybe there's already a concentration of 0.02 grams per centimeters cube. So knowing this, we can calculate the flux J as it relates to the concentration gradient across this thin membrane. And so if we write it out, we can take the difference, C1 minus C2, over the thickness difference, the thickness of this glove, which is X1 minus X2, And if we plug in the values, we can see that the flux or the flow rate of methylene chloride across the thin membrane is 1.155 times 10 to the minus 5 grams per centimeter seconds. Now, this is a fraction of what is considered safe. So even if there's spillage or some drops of methylene chloride that lands on your gloves, you're still okay if you remove your gloves immediately and get a new pair of gloves. We can apply the same type of steady state diffusion calculation to compute the flux whenever we're given the diffusion coefficient for a system with some concentration difference here. So if we're given initial concentration and also a position, and then the final concentration and also a position, we can easily calculate flux using Fick's first law. And this is important to compute in technological examples such as doping silicon with phosphorus to make N-type semiconductor materials. One of the common techniques for it, including phosphorus into silicon, is called ion implantation. And so there, you're diffusing phosphorus. Well, one, you're implanting phosphorus at the layer of silicon, so that you see here. And then that's followed by a heat treatment in which then the phosphorus will diffuse into the crystal structure. And so the phosphorus atoms that are right at the surface aren't necessarily in crystal sites just yet, but after the heat treatment, it'll actually, the atomic structure will actually rearrange and then it'll become crystalline. So the second type of diffusion that we'll talk about is non-steady state diffusion. And so here, the flux is changing as a function of time. And so when we talk about non-steady state diffusion, we'll work a lot with this solution, the solution to a PDE. And the boundary conditions are as so. So for a certain concentration, C naught, in the material, at time t, that's the concentration that's in your system. And we're considering a semi-infinite solid. So what that means is the bulk concentration is just going to be defined as C naught, and you're adding in your diffusing species at the surface, and that diffusing species is just going to diffuse into the bulk over time, but the flux is not constant over time. So unlike steady state diffusion, non-steady state diffusion, for non-steady state diffusion, the flux is changing as a function of time. At some time greater than 0, as we're adding in the diffusing species, we'll know the concentration at the surface, and we call that concentration CS. And the surface is defined as x equals 0. And so here you could see that the flux is changing, over time. And so to just mathematically compare the two types of equation, we have steady state diffusion, where we can use Fick's first law, and that the flux is constant over time. There's no time dependence in this equation. Fick's second law is for non-steady state diffusion, in which there is a change in the concentration gradient over time. And the way we can think about that is, for Fick's second law, we can think about the flux that's coming in on this left side versus the flux that's coming out of the right side over a distance dx. And so if there's a difference in the flux, as in they're not the same, then we can write it as dj over this distance dx here, and the concentration gradient is changing over time. And so we can get the second derivative as a function of, with respect to x for the concentration gradient by writing out j is dc dx, and then dx is just dx. So that's where we get the second derivative from. And the solution to this PD is shown here, in which Cx minus C naught over Cs minus C naught is 1 minus the error function. And if you haven't worked with the error function yet, it looks something like this. In fact, this is actually 1 minus that of the error function. Okay. And we use this as a solution because it fits very well the profile of the change in the concentration gradient over time. And so I'm just going to go back to that. So you can see here, this profile can be fitted quite well with the Gaussian error function shown here. And so for the next few slides, we'll go over some examples on how to use the solution to the differential equation. Okay, let's take a look at the carburization of steel example. So if you have some steel that originally had 0.2 weight% of carbon, and you're going to diffuse carbon into the steel to get a desired 0.6 weight% overall. So what that means is you're starting at the surface, you're adding in carbon, and you continually just add in carbon until you get 0.6 weight% of that carbon at a 1 millimeter distance from the surface. So the surface here, x starts at 0, and then you go a millimeter, let's say here, into the material. And so we can use the solution to the differential equation that involves the error function to calculate the time that it would take to carburize the steel to the desired weight%. So this is the solution to the differential equation. We know that at the surface, you're adding in 1 weight% of carbon, and the initial bulk weight% of carbon is 0.2. And so we can plug in these values. Cx is 0.6, that's the desired amount, minus C naught, which is 0.2, divided by 1.0 minus 0.2, and that is equal to 1/2. Okay. If we move the 1 over, we'll get 1/2 is equal to the error function of z, and this is the z amount. So we don't have a way to exactly calculate this, and so we can extrapolate from data tables. And so the values for the error function are given in table 5.1. So that's shown here. So here you could see 0.5 is equal to the error function. So you could see that that is somewhere in between 0.4755 and 0.5205. So z is somewhere in between, z is somewhere in between 0.45 and 0.50. And so what we can do is a linear interpolation in which we know if the error function of 0.45 is equal to 0.4755 and the error function of 0.5 is 0.5205, then the error function of something 0.5 is equal to the error function of something that's going to be in between 0.45 and 0.5. And so by linear interpolation, we can calculate that Z is 0.4772, and Z is just the diffusion distance, x over 2 square root of dt, d being the diffusion coefficient and t is time in seconds. So we know that the distance is 1 millimeter, so we plug that in there. And the diffusion coefficient is, actually this should be squared. The diffusion coefficient is 2.98 times 10 to the minus 11, and we can compute the time. Now that is if we're given a diffusion coefficient. As you can see in this example, the diffusion coefficient was actually not given. So how did I get there? Well, I know this reacted at 1,000 degrees Celsius or 1,273 Kelvin. And so D is just the pre-exponential factor. So in the data table, it's given as 20 times 10 to the minus 6 meters squared per second. And then you plug in the values for the activation energy, the gas constant, the temperature that you're reacting at, and that gives you D. And once you figure out that D, you can plug that into here. Once again, that should be a squared, not just a 2. Okay, so I'll leave this example for you to practice using the error function and looking at data tables. Okay, let's talk about this solution to the differential equation some more. If we consider the situation in which indium or some diffusing species is diffusing into pure silicon with some concentration X into a depth of X. At a particular temperature, let's say 1600 K, right? Conceptually, what will happen to the value of X over root dt, the diffusion time, and the diffusion coefficient? Well, for the condition in which you're going to decrease the diffusion temperature, so you're going to decrease it from this value, well, what will happen? Well, if you decrease the diffusion temperature, it's going to take you longer to diffuse indium into silicon. The diffusion coefficient will decrease based on the relationship that we've seen before. So if you decrease T, you're going to decrease the diffusion coefficient overall. However, these values will not change because nothing else has changed. So the concentration at X and the initial concentration as well as the surface concentrations have not changed. And so if you're only changing the temperature while the diffusion time is increasing and the diffusion coefficient is decreasing, this overall value will not be changing. Another way that we can use the relationship that is the solution to Fick's second law is shown here. So if you're given a material, let's say copper, and it's diffusing into a bar of aluminum, if you know that it takes 10 hours at 600 degrees Celsius to achieve some desired concentration, you can calculate the time that it would take to get to the same concentration when you decrease the temperature. Okay, so here we can see that if this stays constant and you're just changing the temperature, then your diffusion coefficient, your D's, will change, as you could see here. But then your x over root dt is going to stay the same as we've just discussed. So if that's the case, then we can rearrange this. We can set x1 over, 2 dt squared. Oops, that's not squared. Equals x2, say 2 d1, d2, d2. Okay, so I get squared. These are just, oops, hold on. These are just prefactors, so they'll just cancel each other out. And so if we rearrange this equation, we could see that we can calculate the time that it takes at a lower temperature if we're given the diffusion coefficient at the higher temperature as well as the lower temperature. And we could see that the new time that it's going to take is 110 hours at the lower temperature of 500 degrees Celsius. So you would see what a remarkable difference in time that it takes for copper to diffuse through aluminum when you just decrease the operating temperature by 100 degrees. Here it took 10 hours, and by going down 100 degrees, it's now taking you 10x or 110 hours. Okay. We can also just see this in another example where if you're carburizing steel at 930 degrees Celsius for 10 hours, the carburized death, the diffusing species will distance is 0.04 centimeters. So if you want the depth now to be 0.08 centimeters, we can rearrange the equation to get that T2 is equal to 4 times that of T1. So it's going to take 4 times as long to carburize to a distance of 2x more in this example. Okay. We won't discuss the Kirkendall effect in this recording, but we'll talk about it in the demo at the next lecture. Okay, let's talk about diffusion at the grain boundary and surfaces. We've talked about the grain boundary defects when we were talking about 2D defects in chapter 4. Diffusion of atoms at the grain boundary is going to be much faster than that relative to atoms in the bulk, right? There's dysregistry between the grains, so the atoms aren't aligning as well. The microstructure is a little bit more open as a result of these defects. And so atoms at the grain boundary will move a whole lot faster and hop a whole lot faster than, say, when they're in the bulk. And at surfaces, these atoms have more dangling bonds, the structure is even more open, and so the diffusion coefficient will be higher than that of grain boundaries, and of course that's already higher than that of the diffusivity within the bulk or within the volume of the material. And so we can see that here when we look at the diffusivity plot as a function of reciprocal temperature.